there is a new post on a link and the username, which is my email, and a password for logging to Flow 360. And once you're able to log in, you should see a web page like that. Okay, so what we are going to be doing today is we are going to be talking about what you can look at after you run a CFD computational fluid dynamics simulation. So that's basically we're doing all the post-processing part today, and in the next sessions we're going to be talking about how to launch a CFD simulation. So today we are going to just look at a simulation and analyze the results. All right. Are you able to log into this? Yeah, okay. So let's actually get started. So go to the cases, and there should be a folder called the MIT Aerodynamics 2013. And there are several simulations in this one, and we'll just pick one of them to look at. So all of them, actually most of them are doing calculations on a simple wing that we're actually going to test in the wind tunnel next week. Okay, so that's the shape of the wing, and it's basically a glider wing. And so we'll first start by talking about what the simulation is actually doing. Okay, so a computational fluid dynamics simulation discretizes all the space outside of the airplane, in this case outside of the wing. Okay, and it discretizes in the sense that it splits the entire space into small control volumes, and it solves a bunch of equations that solves the conservation of mass, conservation of momentum, conservation of energy, etc., right, on all of these control volumes. So if you click on the convergence part, you can see like what equations we are solving and how they are converging. So here, for example, you can see the continuity equation. That's basically conservation of mass, right? And over here, it also has conservation of momentum in the x direction, conservation of momentum in the y and z directions, conservation of energy, and finally, the new head equation is solving for turbulence. So that's something we just started talking about today, and it basically tells us how big or how strong the vortice, like the small vortices, unsteady vortices are, that helps transfer momentum in and out of the boundary layer. Okay. And each of these equations are actually not a single equation, but one equation on each of these control volumes. And regarding to how many of these control volumes you have, if you go back to description and click on the mesh ID, it shows you the information about the mesh. And in this case, the number of nodes here is the number of control volumes. So basically, this mesh has 2.7 something million control volumes. So when you are looking at these convergence of these equations, you need to know that all of them are not just the one equation. They are like 2.something million equations we're solving here, and multiply by 6 because we have 6 equations per node. All right. Okay. So basically, the convergence of the equations tells you how accurate the solution is with respect to the true conservation, right? So for example, if you see the mass conservation equation converges to a residual of 10 to the minus 9 or something, it basically tells you that the mass is conserved up to that precision in the final flow solution, right? And similar like x momentum, y momentum, etc., right? So if you see a conservation that only converges to 10 to the minus 6, for example, you'll know that the flow is not as well converged as 10 to the minus 9. And the min-max panel tells you, for example, here in the flow field, what is the minimum density compared to the free stream density, right? So the free stream density is always so this is non-dimensionalized, so that the free stream density is equal to 1. And what's usually most useful is the minimum u velocity magnitude. And this velocity magnitude is non-dimensionalized with respect to the free stream speed of sound. So you can roughly consider that as a Mach number, right? Yes?
I have a question about Mach number. I mean, what are we supposed to do for the licensing?
Oh, if you click on the link on MIT license, you see a very small text file, right? And I think on the second line of the text file, you should see an IP, an address, like an internet address. It says I don't remember, like license 22 at mit.edu or something like that. And then you copy that address. Once you launch Techplot, it'll have several options. Ask you, do you want to do a trial version or you have a license server? You click the license server. And next page, you have a text box to enter that address you copied from the text file. Okay, now let's get to the real useful part of CFD, right? The forces. So if you click on the forces, it is going to tell you, just to make the font a little bit bigger, tell you the lift coefficient, CL, the drag coefficient, CD, and the force coefficients and moment coefficients. Okay, so the lift coefficients are the magnitude of the lift non-dimensionalized by half of rho u infinity squared and a reference area. And the reference area, we're going to, it's something you input when you are launch the simulation. Usually for a wing like this, it is basically the planform area of the wing, serving as a reference area. Okay, and here the lift coefficient is about 1, drag coefficient about 0.05, and the force coefficients are non-dimensionalized exactly the same way. Okay, so can somebody tell me why the CFZ, the z directional force coefficient, is not exactly equal to the lift coefficient CL? One is 1.1 something, the other is 1.09 something. So what's the difference between a lift coefficient and the force coefficient in the z direction? Yeah?
Is it because of the angle of attack? Not all of the lift is in like the direction, there's some in the x direction.
Exactly, it's because of the angle of attack. So if the angle of attack is equal to 0, you should see the z directional force coefficient exactly equal to the lift coefficient, and the drag coefficient equal to the x force coefficient. Now, because there is non-zero angle of attack, right, the lift is always in the direction perpendicular to the free stream, right? And the free stream, it has an x component equal to the free stream velocity times cosine of alpha. And in the z direction, also has a z direction component. The free stream in the z direction is equal to the free stream speed times sine of alpha. So the free stream goes upward a little bit, right? And the direction of the lift points forward a little bit, right? That's why CL is not equal to CFZ. And CD is positive while CFX is actually negative, all right? So CFX has some of the lift in it. Okay. And the moment CMX, CMY, CMZ are the moment coefficients. Yeah, so by the way, CFY is equal to 0, right? Why? Because the wing is symmetric, right? Left and right. The only reason this is not exactly 0 is because 1, the equations are not solved converged to absolute 0, and 2, the mesh is not symmetric, right? So there is discretization error here. How we divide the control volumes are going to have an error. Okay. Similar about the moments, the only non-zero moment should be CMY, the pitch up moment. Okay, and these are how the numbers are converging as a function of the iterations, right? Okay, any questions on this? Now we look at post-processing. So basically this looks at, this is very similar to our our AVL analysis, particularly if you look at CFZ per span, it looks at how the lift distribution looks like as a function of y, right? So this is the span-wise extent, and here we see a almost elliptical kind of a distribution, right? So this is a pretty well designed wing. It's actually designed by Professor Driller in the department. Okay. And finally, go to visualization. It basically is the three-dimensional visualization of this wing. And so let's take a look at skin friction coefficient. So this CF VAC is a visualization of the skin friction coefficient on top of the wing with the direction also visualized. If you zoom in a little bit, you can roughly see the streaks. It's supposed to visualize the direction of the skin friction, right? So the skin friction is the wall shear stress, or the frictional force per unit area, non-dimensionalized by half of rho u infinity squared, right? So that's what CF is. Now, in our two-dimensional analysis in the lectures, CF doesn't really need a direction, because in 2 dimensions we know the viscous shear stress is tangential to the wall, right? Once it's tangential to the wall for 2 dimensions, we don't need a direction. But in 3 dimensions, just the saying is tangential to the wall doesn't mean we know the direction, right? So we also need a direction. In this case, the direction is pretty boring. It just points from leading edge to trailing edge. And we'll later look at a case where there is a flow separation, and the direction is not going to be as boring in that case. Also, the magnitude can be seen here. So this is in log 10 values. So -1 means 0.1. And the -2 is going to be 0.01, right? So if you change the scale, you're going to see the leading edge are going to have a skin friction coefficient somewhere between 0.01 and 0.1, right? So this shows you the magnitude of the skin friction. As expected, is high near the leading edge where the suction peak is, right? We saw today the boundary layer experienced a very rapid favorable pressure gradient from the leading edge to the minimum pressure point. So the skin friction should be very high at the minimum pressure point, and then it goes down as you travel towards the trailing edge. Well, on the underneath of the airplane, the skin friction doesn't change that much, right? So that's that's the skin friction. Okay, any questions on this? So this is looking at the alpha 10 case. You can go back and look at the alpha 15 case, right? I think I just around the alpha 13 case. I don't know if that one had separation or not. So let's take a look. Again, the convergence. The convergence is actually a bit worse than before, right? This is probably a case that's kind of very hard to decide. Is it separating or non-separating? Usually, these kind of cases converges the slowest. Let's actually look at the alpha 15 case, because it's a pretty well separated case. The residuals for separated flow is not as low as the attached flows, but is better than the last case. And the forces, let's actually compare against the several cases. So the alpha equal to 10 case over here, going to also open alpha equal to 13 case, and alpha equal to 15 case. So if you look at the forces, so alpha equal to 10, the lift coefficient is 1.1, drag coefficient 0.05. And for alpha 13 case, lift coefficient increases by a little bit, right, from 1.1 to 1.29. Drag coefficient increases by almost a factor of 2, 0.095, right? And alpha equal to 15, the lift coefficient further increases, but only by a little bit. Drag coefficient again increases massively to 0.13, right? Okay, and then if you look at the post-processing, the lift per span, you want to look at CFZ. You see that along the center you still get quite a lot of lift, but towards the two ends your lift is much lower, right? And then looking at the visualization of the 15 degrees angle of attack, and particularly look at the CF as a vector. So what you see is that there is a very low area of very low skin friction over here, right? Why? Flow separation, right? So when the flow, when basically the layer of fluid closest to the boundary reaches almost zero velocity, the shear stress should be almost zero, right? So this is roughly the line of flow separation over here. And afterwards, there is a shear stress, but like it might be because of the reverse flow, right, in the separated region. And then if you go towards the tip, you see a huge vortex sitting over here, and it turns out that the entire tip is massively separated. So we're going to see a little bit in the volumetric flow later how it is going. So now let's actually, now you have Techplot, right? So if you click the download button, you should be able to download this volumetric flow field over here. And it may take a while depending on your Wi-Fi speed. So just to pick one of the simulations, download the volumetric data. Take a look at how the 13 degrees angle of attack is doing. Okay, the flow is pretty much attached all the way to the trailing edge, but the tip is looks like it's stalled, right? Look at post-processing. I think we should see the same result. Yeah, the tip is the stall starts from the tip for this glider. All right. Okay. So once you download the data, you can load it in Techplot. So let's open Techplot. Open the data and you have to decompress it. There is a volume dot something right inside the compressed file. You have to extract it and put it somewhere.
Where did you download the file from?
You download the file by clicking the download button. You should see a volumes.tir.gz. That's usually the biggest file inside here. Just download that. All right, okay. So once you open Techplot, you can click this. Yeah, so actually go to File and say Load Data. And after you decompress it, the file should be in an extension called SZPLT. And I think by default it's just named the volume.sp SZPLT. So load that file. So here I'm going to load the alpha 15 file. So after you load it, you should see something like that. How fast is your download? Okay. All right. Maybe I'll start walking you through it. Because it's a three-dimensional data, right? So this contains actually all the data of the three-dimensional space around the wing. So how do you visualize the three-dimensional data? So that's what we are going to find out. Okay. So the two most simple way to visualize it is through isosurfaces and slices. So isosurface is analogous to a contour line in 2 dimensions, but it's just in 3 dimensions. So if you have a scalar field in 2 dimensions, right, a contour of that scalar field is the collection of points over which that scalar field is equal to a particular value, right? So that usually forms a closed line, being the contour. But in 3 dimensions, the collection of points on which the scalar field is equal to any particular value forms a closed, not contour, but a closed surface, right? So that's what the isosurface is about. For example, if we turn on the isosurface, and we turn on the isosurface, by default it says Mach number, so it is drawing the Mach number, it drawing the isosurface, drawing all the points on which the Mach number is equal to 0.09. So let's actually make it 0.001, right? So that it is a very small Mach number. What do you think the collection of points on which the Mach number is equal to 0.001 looks like? Any guesses? What's the collection of points over which the Mach number is equal to 0? Right, this is Mach number relative to the wing. Well, we can find out. Right now, we don't seem to see anything, right? So let me actually choose the, let's zoom in a little bit. Okay, now we see something. Let's zoom in a little bit more. Zoom in a little bit more. That's the wing, right? The collection of points on which the Mach number is equal to 0 is actually the surface of the wing. Right, makes sense? Everywhere else in the air, there is a flow going on, right? So basically showing a isosurface where the Mach number is very close to 0 essentially shows the surface, the solid surface. Yeah. Okay, so click on the isosurface and change this isosurface to isosurface of Mach number, first of all, equal to 0.001. And then on the default, you should just see almost nothing or just a point. So you have to zoom in into the point, right? This is because for a CFD simulation, we have to simulate the flow around an airplane as if the airplane is flying at empty space, which corresponds to a domain of infinite size. Of course, we cannot really have a infinite size domain in the computational fluid dynamics, so we draw a domain that's much, much larger compared to the wing, right? So that's why initially you are looking at the very big field and you have to really zoom in to see where the airplane is. Are you able to zoom into the wing? No? Okay, we're going to take a look at, so right now what it shows on top of the surface is the Mach number. Of course, it's very boring, right? Because we are looking at the isosurface of the Mach number equal to 0.01, and you're coloring the surface by that same number. So on the surface, it's all just the black. So let's actually click on the isosurface and click contour and shading, right? On contour and shading, you can flood it by not the Mach number, but a CP, pressure coefficient. And you should see the wing becoming a bit more colorful, right? Okay, and you can say, okay, you can also change the range of the pressure coefficient by setting the levels. So instead of going from -14 to 0, you can set it to let's say -3 to 0. And yeah, so here now you can see how the pressure coefficient is distributed along the wing. So we see
Can you use that last question?
do what?
We're changing the colors.
Oh.
Not the first time, but like how you can break it.
Okay, so isosurface, contour and shading flooded by CP, and you click the button right next to CP. That'll allow you to change, click set levels. That'll allow you to set the maximum and the minimum level of pressure coefficient. Right? We know the maximum pressure coefficient is always equal to 1, right? The minimum pressure coefficient, I don't know, like you can set it to -2, -3, etc. That'll basically the black region is the region over which the pressure coefficient is even less than -2, right? And you can also use all these rotation buttons to rotate the wing, right? At the bottom, the pressure coefficient is high near the leading edge, and the moderate over here. At the top, you are gonna see a very low low pressure region near the leading edge. Okay, so now this is only the surface, right? Another even more useful thing to look at is the slices. So if you click on the slices, okay, you're gonna see a very large region. So of course, when you can zoom out, you can see actually the whole computational domain, right? So this is basically we are slicing through this whole computational domain, and if you click on the like a gear button next to the slices, you can set what slice you want to look at. The default is an x-plane, so the slice over which the x-coordinate is equal to this particular value. What's more interesting is slicing through a y-plane. So if you slice a y-plane where the y is equal to 0, for example, then you are slicing through the center line of the wing, right? Okay, so basically click on the gear next to the slices and set it to go to definition and change the definition to a y-plane of equal to 0. All right. Okay. So afterwards, you can click on this button that says snap to an orientation view. And if we're looking at the y slice, we want to look at the XZ plane. All right, click on the XZ.
How do you zoom out?
So what I did is I clicked this button, the translate button, and hold my middle button, and that'll help you zoom in and out like that. I don't know how to do it on the trackpad. that's why I brought a mouse. Yeah, if you're on the trackpad, that might be a little bit more difficult to zoom out. You might have to click on the view and say fit everything, right? That'll fit everything, and you can now zoom out. So here I click the YZ view, so I'm looking at the YZ axis, and then I can zoom in. Into the center. Okay, so here actually the wing obstructs my view, so I'm going to disable the isosurface. Then I'm basically seeing only the cut plane itself, right? And this right now I'm showing the Mach number over here. Again, I can click on the gear between the slices and go to the contour. Here I can show what I'm displaying here. So here the default is a Mach number, and is actually a good thing to look at. I can also click on the gearbox right to the Mach number and set the levels. So here I'm going to set it from 0 to 0.2. Okay, now I have a good view of the Mach number distribution on the cut plane at the center line of the wing, right? And here we can clearly see there is a little bit of a separation going on over here, where the Mach number is basically uniformly black, right? So we can also see that near the leading edge, there is a region with a quite high Mach number compared to free stream. The free stream has a Mach number of what? Of about 0.1, right? But near the leading edge, the Mach number is clearly way above 0.2. Okay. And we can also see clearly the boundary layer over here, right? So the boundary layer is actually very, very thin towards the leading edge. Like, look at just the whole thing. The boundary layer is over here, right? It's extremely thin. And actually, it's a good thing to look at is actually what the mesh is we are using to be able to do the calculation like this. So again, if you click on the slices, we have talked about definition, contour. If you go to other, and there is an option of show mesh, right? If you click on show mesh, you actually see what the mesh is around this airplane. So again, like this shows you also the grid points, and we are solving basically we are solving 6 equations per grid point, right, for calculating that flow field. And one of the things I think is worth pointing out is how the mesh gets finer and finer towards the wall, right? So every time you get closer to the wall, the mesh becomes a little bit thinner, usually by a factor of like 10 to 20% smaller towards the wall. And that allows you to really resolve this very, very thin boundary layer, right? So just to look at how thin the mesh is, this is the thinnest mesh at the wall. It's very thin compared to anything outside of the boundary layer. That's what allows you to actually capture how the flow changes as you move away from the wall. Yeah, any questions? Okay, so that's you can also see how the boundary layers becomes thicker and thicker as it so when you see from the very high Mach number region, as you go downstream, the boundary layer is constantly being subject to an adverse pressure gradient, right? So basically, the velocity outside of the boundary layer gets slower. It means the pressure is increasing along the way, and the boundary layer thickens very significantly as it moves towards the trading edge. And finally, it separates. All right, let's disable the mesh. Okay, another thing we like to look at is go back to the definition. Here we are looking at a y equal to 0 slice. So let's move towards the tip a little bit and look at how the flow separation is different towards the tip. So if we change from 0 to 10, right, we see a different cross section, but the flow is pretty similar. Go to 20, again the flow is still pretty similar. Go to 30. Okay, at y equal to 30, the flow field is now massively different, right? So if you remember looking at the flow field, not the flow field, look at the post-processing, right? At 20, it's over here. The lift is still pretty high, but at 30, we start to see this dramatic drop in the lift, and this is why, right? Instead of separating at over 50% of the chord, the flow separates almost right at the leading edge, like right over here. Right? Are you able to see this? Any questions you have in manipulating the views on the flow field? So I guess looking at something different. Can I help with you? Right. So this is basically clicking on the slices again. Go to the definition. Look at the y-plane of y equal to 30 instead of 0. Right. I'm still looking at Mach number here. Of course, you can look at something different. You can look at, for example, pressure coefficient (Cp). Right. You're gonna see like Cp is very low over here, and it's the increase in the Cp, right, adverse pressure gradient, that causes the flow to separate at the leading edge. All right.